represent Wei-Wave, an adaptive imaging technique for wavefront sensing. Consider a spherical wavefront denoted by U. Conventional sensors measure light intensity, that is, absolute value U squared, which in this case results in a uniform image. However, what is not captured is the phase of the light, the angle of U, an important optical attribute that is related to the distance light traveled. Wavefront sensors capture both the amplitude and the phase of an optical wavefront. For example, one such device is known as point diffraction interferometer. The idea is to take an incident wavefront as input and split the wavefront into two copies using a beam splitter. One copy of the wave refracts off a mirror, resulting in a wave that retains its original shape, so the sensor receives our original field U. The second copy refracts off a small pinhole, which turns the wavefront into a planar reference wave R. These two wavefronts interfere at the sensor, which measures the sum of intensity of U, R, plus the real part of real R conjugate. In this setup, R is none, as it is a simple plane wave. Therefore, we can isolate the complex field U and then recover our missing phase. This provides a very elegant solution, instead of the fact that, since we place a pinhole, most of the energy in the reference wave is blocked, and the resulting reference wave is very dim, making this approach very sensitive to noise. Our goal in this work is to open more than a single pinhole to collect more light. However, when we open more pinholes, the reference wave becomes non-planar and its shape is unknown. Recovering it becomes a non-trivial wavefront sensing problem of its own. Our main contribution is in proposing a strategy for the selection of the host for the reference wave, which we call a collision-free layout. This lateral layout facilitates an analytic reconstruction of the reference wave despite the fact that it is no longer a plane wave. For more details, please refer to our paper. We have built a lab prototype to optically implement our rewave method and have several applications. Here we capture the phase of the wavefront, propagating through a microscope slide. Once the amplitude and phase are known, it is possible to refocus the image of this light by propagating the wave to planes at different depths. For example, here we visualize the amplitude of the wavefront at two different depths, each showing a different cell in focus. Rewave can also measure a clear phase pattern of a Fresnel lens, which is a phase mask with quadratic pattern as shown in the bottom left. When we zoom in, we can clearly observe the quadratic phase pattern across this phase image of the Fresnel lens. We can use this information to form high-resolution images of a target with nothing but a cheap Fresnel lens. While a Fresnel lens attempts to focus the light, it is very low-quality lens, and the image it forms is subject to many aberrations as we demonstrate here. However, with our rewave setup, we can measure the phase of the Fresnel lens precisely. We can then use this phase to correct this wavefront and recover a clear image of the resolution chart. Thanks for your attention, and please refer to the paper for more details.